Okay, 8.13 is arc length. So it says the idea behind finding arc length is very similar to the way we find area using calculus. We are going to divide the curve into large quantity of small segments, find their lengths, and then add them up. In order to do this, we need to recall the distance formula from algebra, and that is distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So it says we can approximate the length of a graph of a function f by using inline segments whose endpoints are partitioned between a and b. And it says think of this as a being x sub 0 and b being x sub n, where the numbers between that would be x sub 1, x sub 2, etc. This is telling us how many small segments we are using to calculate the distance. So on your guys' notes, since you don't have it color-coded like mine, go ahead and get a different color pen or highlighter and highlight where on my notes there's red. So while you guys are doing that, you don't need to write what I'm writing, okay, is if we were to find the distance, let's say from point A to point B. So this is point A to point B. And then someone was like, well, that's easy. I can just connect that. And that would be the distance between the two. So nobody's drawing this. We're just discussing. Okay. Would this be an accurate depiction of the distance? No, because it's not accounting for this dip in the curve. Okay. So in order to improve that, they use the distance formula on many small segments. Okay, so now you can draw this part. Okay, so I'm starting here at A, and I'm ending here at B. And let's say I had one segment that goes from here to here, okay, and then I draw a line. Okay, we're going to call that first segment where it ends x sub 1. Okay, and let's say I make another one here, connect those lines, and that is x sub 2. And then I do another segment, connect the line, x sub 3. And then let's just say I connect this last segment here. And so really B is x sub 4. Okay, and if you wanted to go back, you would say A is x sub 0. Okay, the very beginning of these segments. Okay, so instead they're saying, well, since we separated this into 4 segments, if we were to find the distance of each of the segments and then add them together, would this be a better depiction of the distance between A and B? Yeah. Yes. So the reason they say that this is similar to us finding the area using calculus is this is the same thing we did in the beginning before we learned about integrals. Okay, we did the Riemann sums of adding all the areas of as many rectangles as we could to get an approximation of the area under the curve. So here someone already did that for us and found a formula on how to convert arc length using integration. So it says if a function y is equal to f of x represents a smooth continuous curve on the closed interval a to b, the arc length of f between a and b is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. Which means when we are given these types of problems, in order to find arc length, they're going to give us the original function. We're going to have to take the derivative of it, square it, and plug it into the integral before we can integrate. So for example, number 1 says find the arc length of the graph y is equal to 1/12 times x squared plus 8 to the power of 3/2 from x is equal to 1 to x is equal to 4. So right away, it gives us our bounds for our integration. Okay, so it's going to be the integral from 1 to 4. what we need to find is the derivative. Okay, so remember, when we're finding the derivative, okay, everyone should know all their properties of derivatives already. But if you forgot, this is going to be the power rule and the chain rule, because we have to take the derivative of the outside function and then multiply it by the derivative of the inside function. So this becomes 1/12 times 3/2 times x squared plus 8 to the 1/2 times 2x. Okay, so again, that is us using the power and the chain rule. We can simplify this because this 2 will cancel with that 2. And this 3 and this 12 can reduce to 1 and 4, which means I have x over 4 times x squared plus 8 to the 1/2. Okay, so that's my first step, is to find the derivative. My next step is to square the derivative. Okay, so that is x over 4 times x squared plus 8 to the 1/2 squared, which means I get x squared over 16 times x squared plus 8 because the 1/2 and the square cancel. Okay, everyone with me so far? Okay, now I'm going to take that function, that derivative that I squared, and I'm going to plug it into my integral. So I have the integral from 1 to 4 square root of 1 plus x squared over 16 times x squared plus 8 dx. Okay. Now from here, this is our integral already set up for arc length. Okay, let's say you had to solve this by hand. So I'm going to show the steps just on this first one, because you're going to have to manipulate the problem in order for us to get it to a way that is easiest to integrate. So the first thing I would do here is I want to get rid of that divide by 16, so I'm going to multiply everything by 16. So I have the integral from 1 to 4 square root, and if I multiply everything by 16, really I changed the problem. So in order to not change the problem, I'm going to multiply by 16 and divide by 16. Okay, so really I'm multiplying by 1. So this is 1 over 16 times 16 plus x squared times x squared plus 8 dx. Notice I multiplied by 16 to get that fraction out of there, but I still in the very front divided everything by 16, so really I didn't do anything. Okay, I multiplied by 1. Okay, the reason I did this is I can now take out the square root of 1 over 16 because that's what? 1/4. So this is 1/4 integral of 1 to 4. And then I can just simplify this by distributing the x squared. And I get x to the 4th plus 8x squared plus 16 under the square root dx. Okay, so far it's getting easier and easier. Okay, slowly we're getting to a point where we're going to be able to integrate. The next thing I want to do is try to get rid of that square root. Well, if I look at x to the 4th plus 8x squared plus 16, I notice that this is a perfect square. Because we all know our algebra, right? Yeah. So 1/4 integral of 1 to 4 square root of x squared plus 4 squared dx. It's a perfect square.
X squared plus 4.
Yes, because the square and the radical cancel out. So now I have 1/4 integral 1 to 4 of x squared plus 4 dx, which is a lot easier to integrate now. Okay, and for the rest of those steps you could do on your own. You could integrate it and solve from 1 to 4, and you get 33/4 as your answer. Okay, so you may have to manipulate your integrals in order for you to be able to integrate it in the first place. Okay, Okay, of course, there's thousands of ways you could solve this. You could try, let's say, u substitution to also try to simplify. Just know that that may not always work. Any questions on one? Okay, last one, number 2. Says set up an integral that represents the length of a curve, y is equal to sine x, from 0 to pi, and then use a calculator to find the value. So it just wants us to set up the integral. So the first thing we need to do is take the derivative. So what is the derivative of sine of x? Cosine of x. And then we have to square our derivative. So what's the square of cosine of x? Cosine squared x. Then we plug it into our integral. So the integral from 0 to pi, square root of 1 plus our derivative squared, which is cosine squared x, dx. Okay, notice we could simplify this by hand if we knew all our trig properties. Okay. It would have been sine squared of x is the same as 1 plus cosine squared of x. The square and the square root cancel, and so you're just left with sine, and sine of pi minus sine of 0. But this allows us to use a calculator, so we're going to use Desmos. Okay, and when you do that, you get 3.820.